Hey everyone, I'm Alejo Sutro. I'm a staff privacy analyst,
And I'm Shankar Garikapati. I'm a staff privacy engineer.
and we're from Lyft, here to talk to you about how we worked through user data deletions and exports for the California Consumer Privacy Act, or CCPA. For those of you who haven't seen us before, Lyft is a rideshare and transportation company. Our core business is connecting drivers with people who need rides. For a lot of our users, that's what Lyft means to them, but we actually do a lot more than that. We operate a vehicle rental program called FlexDrive for people who want to drive for Lyft but don't own a car yet. We also offer rental cars for personal use too, and we operate a network of bikes and scooters in dozens of cities around the world. It's a lot of data to wrangle across all those lines of business. We have 18 million riders on our platform. There are over 1,000 microservices that power everything we do. Plus, we've been at it for over 10 years. And then there's all the stuff most people don't think about that you still have to do in order to run a business like ours. We buy insurance for people while they're driving on our network to help protect them and their riders. We have to process payment information for completed rides, and that comes with chargebacks and fraud and all sorts of edge cases and weirdness. Sometimes our scooters decide to go swimming, and we have to go find them and dry them off, give them a little pep talk, and get them back out there. It takes a lot of data to make all that happen. And getting privacy right is super important to us at Lyft, but it's a big job. And CCPA added new dimensions to our big data problems. The thing with the California Consumer Privacy Act was that it wasn't a task to complete and move on from, but a beginning of something bigger, both in privacy legislation and privacy at Lyft. CCPA was the first state level legislation passed in the United States, and it followed on the heels of Europe's General Data Protection Regulation, GDPR. There have since been laws passed in Utah and Colorado, Virginia, and Connecticut, but CCPA really set the stage in a big way. It called for companies to give their users a wide range of privacy rights, and we won't have time to cover it all today. But let's zero in on just these ideas of data export and deletion. Now, export and deletion can seem really simple, but actually, there's a lot of complexity that had to be ironed out for an organization of our size and scope. First of all, our solution needed to be holistic. We talked about how Lyft offers a wide range of services, but each of those services have their own special quirks and needs. Early on in our solutioning, it felt like whatever we came up with, there was always some outlier, some part of the company that couldn't fit that mold, and we had to adjust our approach. Then our solution needed to be secure and useful. I'm sure a lot of you are already familiar with security issues. We're not so different here in privacy, right? Like if you're preparing an export of user data, that's a pretty sensitive target for bad actors, right? But it also needs to be secure in that it's reliable. It has to work. Finally, we had to balance all sorts of competing needs and gotchas while we were working on export and deletion. Business functions, from product and finance to trust and safety, all rely on data being available or structured in a particular way. And deleting data can threaten stability. Like, we can't have people deleting their accounts halfway through a ride. Now take that and multiply it by 100 edge cases like that. And you can see where a lot of negotiation would have to happen in order to deliver effective export and deletion. So I'll hand things off to Shankar, who can fill you in on the technical details of how we built an export and deletion solution for our users.
Thank you, Alejo. I would like to start with providing some background on our infrastructure that is relevant to our presentation. At Lyft, we primarily run our software on AWS and use microservices-based architecture with services interacting with each other using RPC calls. Our product teams have a high degree of freedom in designing, building, and managing their services. Teams are responsible for all the technical aspects of the software they build. If you recollect, the strategic goals we had to solve were a one-size-fits-all solution, build a secure, reliable, and usable solution, and balancing competing needs. Let's start with some considerations around developing a one-size-fits-all solution. We ideally want to have a common API with one standard SLA requirement that can be met by a diverse set of services, even though they may be using different kinds of underlying infrastructure. Very early on, we considered and quickly discarded the idea of building a single service that has access to all the data stores. This would be very dangerous for many reasons. We can't anticipate all the possible interactions beforehand, and therefore any repercussions of deleting that data without the knowledge of the local context. This practice is also dangerous from the security perspective. The potential collateral damage for any intrusion to this central service can result in unwanted access or deletion of customer data. A completely decentralized solution isn't an option either. This would be a problem because each team might end up having a different implementation, with each taking different functional choices to address their unique challenges. It also it would also be very expensive from technical perspective to build and manage such a system. Using a shared responsibility model was the key. We, the privacy team, defined the high-level governing principles and outcomes and expected the product teams to use their good judgment in executing them. We also built tools and services to make it easy for them to meet those requirements. So, what does this mean for our data deletion and export service? Federated architecture is a natural choice that meets the shared responsibility model. A central orchestrator is responsible for the end-to-end lifecycle management of a data export or a data deletion request. It breaks down a data deletion or a data export request into a sequence of tasks with their inputs or outputs connected to each other. These tasks are defined one for each service, dictating a particular outcome. Using these tasks as building blocks, a request is processed and moved to completion. The central orchestrator uses a simple state machine to model the task dependencies and uses a series of asynchronous requests to dictate the outcome from the services. It also monitors these services and, if needed, uses mechanisms like retries to ensure progress is made for every request. Product teams that manage customer data implement simple APIs to respond to these requests. By having these teams to work closely with the data, make their own independent determination, helps us to meet unique challenges of each service and or its data stores, but still meet the high-level privacy goals. Here is the high-level overview of the system depicting erasure request. Orchestrator, depicted here in blue color, receives the erasure request from the customer. It performs a sequence of checks with a small set of services, which we call as sanction endpoint services, depicted in purple color. Once all the checks have passed and the determination has been made to allow the deletion, it extracts the list of services that host the customer data from a data store catalog service. Then, using this information, the orchestrator service generates events for these services to respond to. The response can be either deleting the data or extracting the data. I know we haven't talked much about the sanction endpoints or the data store catalog. Some of you might have also noticed we handle requests to offline data store like Hive and Presto little differently. We will also talk about each of these aspects in more detail in the next few slides. Here is a high-level overview of our export system. If you observe, it is very similar to the erasure workflow. In fact, it's the same system. It only uses different kind of events to handle export request. The biggest difference you see here is that in the erasure request, there is no need of any staging environment to store data. In the export request workflow, there's a data staging mechanism where the data from all the services are stored temporarily before ultimately delivering to the user. To ensure that each of these services can independently evolve, we use protobuf as our data serialization format to store and transfer data. Now that we have our one-size-fits-all solution, let's think about our second goal, building a secure, reliable, and usable solution. If you recollect, it is a data store catalog service that provides the orchestrator with a list of services from which to extract or delete the data. This information must be up to date and accurate so that we can push user request events to applicable systems. In such a complex system involving hundreds of services, this kind of problem can appear in many places. For this reason, one of our strategic goals was to ensure that all interactions with the product teams are designed for safety and usability. Developers will make mistakes. They may forget to follow some steps during their product development. And so we want to utilize automation and validity checks where possible. We also have to rely on the principle of least astonishment in designing these systems. That means reducing the cognitive load on the developers. We wanted our naming conventions to be meaningful and easy to use. We wanted our abstractions to be non-leaky. The solution to meet these goals was to bake privacy into the software development lifecycle. Rather than having privacy as an afterthought or as a gating mechanism before launching, we wanted to make sure privacy is considered at each stage. Product teams incorporate privacy metadata tags into their code. For example, the Terraform modules are enhanced to include privacy tags. Visualizations and code organized into modules made it easy for developers to understand and build a mental model of the system. This helps them clearly understand the aspects of the system that they are responsible for and ensure the operational workload and the on-call support would be shared with the teams uniformly and not cause burnout for any teams. We focused on a single source of truth as a guiding principle, which means developers don't have to declare the same set of tags at different places. We have a set of privacy checks baked into our CI/CD pipeline to ensure any omissions or mistakes of this metadata are promptly identified and fixed. All this information is extracted and hosted by the data store catalog service. We also have other privacy auditing infrastructure that exists outside this process to make independent assessments and minimize mistakes. We build libraries for service teams to use that harden the API interactions with the central orchestrator service, making it easier for them to build new integrations, build observability dashboards. We also have runbooks for teams to triage and fix issues quickly. Product teams have used their learnings to improve these shared libraries, thereby benefiting all the teams. Let's talk about our final strategic goal of balancing competing needs. We all know that every business has to manage a host of competing needs. Similarly, in Lyft's case, there can be complicated situations whereas users' erasure request can't be done right away. This can be for reasons like a rider having pending payment to be processed. It's the product teams, like the payment service in this stated example, that have very good understanding of how those requests can be processed. To accommodate this need, we implemented an easy to integrate interface called sanction endpoints, which the product teams use to enforce such checks. In some cases, especially flagged by our legal team, we have to retain data even after an erasure request is being made. In those situations, we might copy the data into a highly secure and purpose limited vault just before the original data is deleted. We glossed over the details about the interactions with offline data stores in the system design slide. Extracting or deleting data from offline resources using a request response model is not feasible because of the impedance mismatch. For example, deleting data from offline data stores effectively would need a complete rewrite. We abstract this complexity from the central orchestrator service, which interacts with all the services in a request response mode by adding an additional layer of abstraction. We add a new service called Analytics Orchestrator for this purpose. It acts as a proxy between ETL jobs that performs the actual extraction or deletion and the central orchestrator service. There were other additional challenges with offline data stores in particular that we need to be very mindful of. First, the issue of whether to execute a particular deletion request exactly once or at least once. Offline data stores are mostly secondary data stores that store a copy of the data created in the online data store like DynamoDB. Data generally flows through multiple hops across various systems before landing into the offline data store. Deleting data once may not be sufficient, since some data may be in transit at the time of deletion. For this reason, deletion ETL jobs also include past deletion request as an additional guarantee that the intended data is deleted. Second, the ETL jobs needs to be designed for failure. A single ETL deletion job can generate hundreds of Airflow tasks, and this comes with significant cost. A complete rerun of an ETL job for a single task failure may not be feasible. Mechanisms like checkpointing can help recover quickly and not throw away a lot of work. Failure of destructive operations like erasure can have the potential to cause data inconsistencies with partial erasure and dangling pointers. We focused on implementing idempotency using techniques like creating backup tables and pointer swapping operations to support consistency. Now, coming to some of the lessons we learned along the way. The most important takeaway is to avoid things like consensus protocols or two-phase commit to synchronize actions across various services. They introduce significant complexity into the system and require each participating service to implement complex protocols. It also makes it harder to onboard or offboard services. It might need more coordination between teams and may not scale beyond a certain number of clients. Instead, we found success in having a simple workflow management system that organized export or deletion into sequence of tasks. The second lesson I would like to share is to plan around uncertainty. Systems and users' behavior is unpredictable. You might experience issues that you could never plan for. What do you do if a team deprecates a service without notifying you? What happens if a ticket is filed for faulty service but no one reacts to it? And or there's no remedy to it? These were situations we predicted and accounted for in our architecture. And the last one, which is true for managing any large-scale distributed system, is to have a robust observability infrastructure to capture end-to-end signals. So I'll hand things back to Alejo to summarize our experience building this service.
Thanks, Shankar. And I know what you all are thinking at this point. So then what happened? Well, the rest is epilogue. We built it and launched it. At the beginning of 2020, the export and deletion systems went live and began serving Lyft users looking to exercise their privacy rights. Of course, we're continually improving these systems and integrating new products, but most of that operations happened in the first 12 months. We got that one-size-fits-all solution by using a federated architecture that could work for all our different microservices. We were able to shift left a lot of the privacy concerns from late stages of the product development lifecycle to earlier ones to save time and effort and headache. We got reliable and usable infrastructure by developing that event-driven model and giving microservices the flexibility they needed to take care of user requests when it could be minimally disruptive. And finally, we were able to balance those competing needs by having a granular and careful stepwise process. It was fault tolerant, non-blocking, and used idempotent actions that were easy to reason about, while data that absolutely had to be retained for a very limited purpose could be vaulted. And all that planning paid off. This was a really big win for us because it was so important that we do this without disrupting the whole company. Distributed coordination among so many teams and services would have been really tough, and coming up with the right engineering approach made all the difference. We managed to scale effectively by mindfully developing this system that played to Lyft's strengths, like diversity of services and technical configurations. Throughout the process, we were able to achieve excellent observability. Carefully tracking each step of these processes gave us the information we needed to troubleshoot problem areas and fix them quickly. And resilience, where no single point of failure in this new infrastructure could threaten the integrity of core business systems. Thank you so much for tuning in to our presentation. Just a quick plug for the team, Lyft is hiring in the US and Mexico. If you're passionate about privacy and security by design and building the infrastructure that powers it all, think about joining our team. We're at lyft.com/careers. Thanks again.